Hello everyone, my name is Yuqing. This is a video presentation of our paper Adaptive Dimension Reduction and Variational Inference for Transductive Few-Shot Classification. This work is funded by Orange and collaborated with EMD Atlantic and Lapstick in France. In this presentation, I will firstly talk about the context, the general few-shot setting, and the limits of the current state-of-the-art methods. Then I will talk about our proposed algorithm in detail, and finally we draw the conclusions. My co-authors of this paper are Vincent Kipon and Stefan Bateau. Few-shot learning studies the problem of building models with limited data. The goal is to achieve decent performance without large resources. The motivation of few-shot learning is very appealing because humans can show abilities to distinguish different objects with just few samples. For instance, here in figure 1, given just 3 examples of a novel concept, tufa, boxed in red, most human learners are able to select just objects boxed in gray. In real-world applications, few-shot learning can be applied to various scenarios with rare cases such as medical imaging. And most importantly, learning with limited data can reduce data collection effort and computational cost, which present a huge advantage for the industry. In this work, we will tackle one common application in the context of few-shot, which is image classification. And the goal is to build a classifier that is able to predict class labels based on very limited data. Here we show an example of a few-shot scenario in image classification. We define a few-shot task that consists of a superset and a query set. The superset contains k number of classes and s number of label samples per class, and the query set contains a total of q unlabeled samples to be predicted class labels. Usually we have very limited number of label samples per class, for instance 1 or 5, and the goal is to build a classifier based on those label data and evaluate on the query set. There are 2 standard few-shot settings that are generally used by the related works: inductive setting and transductive setting. Inductive setting is supervised, and we only have access to the label data in the support set. Transductive setting is rather semi-supervised. In this setting, we not only have access to label samples, but also unlabeled samples in the query set. The advantage of having access to unlabeled data is that we can use their structure to build a better classifier. For instance, here in figure 4, in transductive setting, the diffusion boundary is established only based on 3 labeled samples per class, while in transductive setting, it takes into account the structure of unlabeled samples as a plus. In this work, we mainly tackle the problem of few-shot image classification in the transductive setting. Existing methods in tackling few-shot image classification include the use of a base data that contains a large number of labeled samples per class, and the classes in base dataset are distinct from the classes in the few-shot tasks. The rationale is to learn a model with a large dataset that can be further applied to tasks with limited data. In terms of how to learn the model with the base data, we further identify 2 mainstream methods: metalearning methods and transfer learning methods. In metalearning methods, the goal is for the model to learn how to perform image classification in few-shot scenarios specifically. So the base data in this type of methods is firstly regrouped into a bunch of training tasks that have the same form as the few-shot tasks. Then we train the model with these training tasks. While in transfer learning methods, the goal is to focus on learning the knowledge of the training data, and we train the model the normal way using base data in the form of mini-batch. In this paper, we focus on methods based on transfer learning because transfer learning is simple to implement and they tend to give better performance compared with other learning methods. So the principle of transfer learning is to learn a feature extractor using the base data. Then we fix the parameters of the pre-trained model and extract features of the few-shot task before building an adapted classifier for those features. In this work, we operate on features that are extracted from a pre-trained neural network. The current state-of-the-art method mainly contains three following limits. They have constraints on the covariance matrix when estimating a cluster. They often require class-balanced prior. They often have a fixed cluster parameters, which give less readiness for dealing with uncertainty in a cluster given field data. Especially for the second limit, in which we have a non-deterministic distribution among classes, the fact that we use the prior knowledge about the number of unlabeled samples per class is often not realistic for real-world applications. And recently, a newly proposed unbalanced transductive setting has been reintroduced, in which the query samples are generated according to Dirichlet distribution, so that we cannot know the query set distribution. So for example, if we sample a point which ends up here and gives us 0.2, 0.2, 0.6, this will be the proportion that is used for sampling query samples. Under this unbalanced setting, we can see from table 5 that the current SOTA performance dropped quite a lot. Therefore, we need better solutions to tackle the imbalance. Here we introduce our proposed method, BAVA-. Recall the limits of the current SOTA methods. Therefore, we need new desirable assets in order to better estimate the clusters. Firstly, we need less constraints on the covariance matrix because they may not always be isotropic in the form of a circle. And also we need methods that are able to manage the imbalance. And also we need to cope with uncertainty caused by field data, because when we estimate the cluster parameters, they might not land exactly in the place, but in a range of. Therefore, here we recall the assumptions on the model that a clustering method needs to deal with. A Gaussian mixture model with covariance matrix, a Dirichlet distribution for class proportions, and prior on the cluster parameter. There exists a method called Variational Inference that can fit well in the profile. Firstly, would the VB model regards cluster parameters as variables that can have their own priors? So here we denote theta to be the cluster parameters that include the mixing ratio pi, the cluster centroid ck, and the covariance matrix sigma k. Given that they are variables in a VB model, they have their own priors. For instance, here the mixing ratio follows a Dirichlet distribution, and the Gaussian distribution for the cluster centroid, and Wishart distribution for the covariance matrix. And the goal of the variational Bayesian inference is to approximate the posterior with a distribution Q. The idea is basically to estimate the distribution on the parameters, and the posterior follows the same distribution as prior. For example, here the distribution of the mixing ratio given samples X also follows a Dirichlet distribution, and the same for the two other distributions. Similar to other clustering methods, VB inference also operates under an expectation maximization framework. So in the E step, we compute the cluster assignment, and in M step, we estimate the cluster parameters. To be precise, here in VB, we estimate the parameter distribution using its prior instead of estimating directly these parameters. Given these new desirable assets, the first solution that we propose in BAVA- is variational Bayesian inference. The method gives less constraints on the form of covariance matrix, and it is able to cope with different level of imbalance. And most importantly, it regards some cluster parameters as variables, which gives more flexibility in estimating a cluster. However, there's a drawback of VB model for dealing with a few-shot task, because typically we only have 75 or 100 data points in a few-shot task with 640 dimensional feature space. So when the number of data samples is much lesser than the number of features, this could cause the overfitting problem, and also a large dimensional feature space would introduce noise for the model. And here we can see that when we perform a VB model in the full dimensional feature space, the performance collapse with respect to the baseline performance using k-means. So we need feature dimension reduction methods in order to reduce noise and also reduce the overfitting effect. So in our proposed Baba-Dash, we also propose to use feature dimension reduction, and we apply PLDA, which stands for probabilistic linear discriminant analysis, that uses base data to help find reduced space. And so the dimension of the feature is reduced from D to K minus 1, in which D stands for the dimension of the features and K is the number of classes. And also the features in PLDA would be whitened in a reduced space and become an isotropic covariance matrix in terms of their distributions. So here in figure 8, we can see that the projected features are more isotropic, and they are more separated than the features in the full dimensional space. Also from table 2, we can see that the performance of Baba-Dash in a reduced space is much more improved than the above two methods. To summarize, our proposed solution uses variational Bayesian inference and feature dimension reduction with PLDA. And the algorithm goes like this. We have samples X, and we need to calculate the posterior P data given X. And firstly, we initialize RNK, which is a cluster assignment using soft k-means, and we iterate until values no longer changing. In each iteration, we firstly project the samples into reduced space using cluster assignments. Then we update the cluster parameters in reduced space. And finally, we update the cluster assignments in reduced space as well. Here in figure 10, we show the performance of Baba-Dash on MiniMatchNet, along with a list of other state-of-the-art methods under the unbalanced setting and the balanced setting. We can see that the Baba-Dash reached the highest performance in the unbalanced setting. Also, we reached competitive performance in the balanced setting without using any class balance prior. And note that our proposed Baba-Dash also reached SOTA performance on many other few-shot benchmarks. To conclude, our proposed Baba-Dash used refined VB integrated with adaptive dimension reduction, and we reached SOTA accuracy on nearly all few-shot benchmarks in the unbalanced setting, as well as competitive performance in the balanced setting without any class balance priors. There's a limit, however, is the assumption of a fixed isotropic covariance for all clusters, so we encourage the future work to study for a better covariance matrix estimation associated with each cluster, and we encourage also the communities to continue the few-shot classification in the unbalanced setting.